Last time we were studying chapter 2, right? Heat conduction. And the last numerical that I solved in the class was this one. Okay? And there was some calculation mistake in this numerical. Okay? So I'm going to solve it again for you. And then we are going to finish chapter 2 today, and then also going to start chapter 3. Okay? So chapter 2 is almost finished. There is not much, and let's start chapter 3.
ถ้ารถมันรถพวกแก๊ปอะไอ้พวกโซดาเป็นมอเตอร์ไซค์ก็เลยว่าไปนะ
กูเนี่ย
ไหนนะ
กูเนี่ย
ทำไม
มึงก็ไปกับกู
ไปไหน
ไปแข่งเดี๋ยวก็
เคยนะ
ก็มึงจะไปเดี๋ยวก็ไม่เอาก็ไปของกูไง
Okay. Before this,
แล้วมัน
we also solved this numerical. If you remember.
ไม่แต่มึงส่งที่เดียวกันไม่ใช่เหรอ
ส่งที่เดียวกัน
This one.
ก็ผมส่งที่เดียวกัน
Okay. This one.
ไม่ทำเป็นแยกเป็นเฉย
This question asks the differential equation.
ใช่
Please focus. Don't talk.
ส่งคนละที่อ่ะ
วิ่งงงรายละเอียด
ส่งโปรโพส
ลงซ่อมไปมีชิ้นงานใช่ป่ะชิ้นงานไม่ทำชิ้นงานจะไม่ต้องทำ
So we were solving this question last time, right? And I think some of you had some doubts over this one. Why did we use this differential equation to denote the heat transfer in this case? If you read this numerical, it is saying consider a steel pan. Okay, this pan that is given, placed on top of an electric range, placed on top of an oven. Okay, and they are cooking spaghetti. The bottom section of the pan is 0.4 centimeter thick, has a diameter of 18 centimeter. The electric heating unit on the range top consumes 800 watt of power during cooking, and 80% of the heat generated in the heating element is transferred uniformly to the pan. Assuming constant thermal conductivity, obtain the differential equation that describes the variation of the temperature in the bottom section. Okay. So some of you had a question that why we are using. So this differential equation is for which shape? Plane, circular, or spherical? This differential equation is for what shape, what coordinate? This differential equation is for a plane ball or a sphere or a cylinder. I'm not asking about the question, I'm asking about this differential equation. Plane ball, right? Why we are using a plane ball equation to describe the heat transfer in this pan? The bottom of the pan is circular or cylindrical. Then why are we using this? This is correct, by the way, this is correct. But why? So this question is asking us to provide the differential equation that can explain the heat transfer at this pan. Okay? Why are we not using this third one, which is for cylinder, or this for sphere? Why are we using a plane wall for a pan? Because the pan is placed above the stove, right? The heat transfer is happening in one direction, only in x, right? And the heat transfer is happening in x direction. When you are studying heat transfer in a cylinder, the coordinates are I, phi, theta, right? So the heat transfer will not happen in our direction. The heat transfer will, though the shape of the pan is circular or cylinder or spherical, the heat transfer is still happening towards the thickness, right? The heat transfer is still happening towards the thickness. The thickness is 0.4 centimeter. This is this much thin, right? So the heat transfer from the oven to the spaghetti, which is inside the pan, will happen in this direction, in x direction, not in r, not in phi, not in theta. Understand? Understand? That's why we are using the plane wall. Okay.
คือตามนั้นไปทำที่ตรงเนี้ยปกติในคนเข้าใจไหม
Then, okay, I will maybe revise a little bit. So first chapter we studied basic definitions in the heat transfer subject. Okay, thermodynamics law, heat transfer law, conduction, convection, radiation, all types of heat, right? And in the second chapter we are studying heat transfer by conduction in detail. Okay, so we are first studying heat transfer in different shapes. All sort of heat transfer in any object can be classified in three categories, in three shapes. It's either going to be a plane wall or a cylinder or a sphere. If you are studying heat transfer in a window, in a glass window, you can consider it as a plane wall. If you are studying heat transfer in a bottle, you can consider it as a cylinder. Okay? So then we obtained, then we derived some equations, right? So these equations are general equation for a shape which is a plane wall, a cylinder or sphere. Okay, heat transfer is happening by conduction only. All right. So whenever you are designing a window, a plane wall, you will use the heat transfer equation in the plane wall. Okay. Then there are five type of equation for each shape. Okay, so you have to read the question very carefully if they have heat generation, if it's a steady, right, if the thermal conductivity is constant or variable. Depending on that, you will use the right equation. Okay, so like this one, this was for plane wall, right? This is variable conductivity, K is inside, right? You take the K outside if the thermal conductivity is constant, right? Then three more equation again for the plane wall: steady state, transient, steady state, no heat generation. Alright. Same for the cylinder and sphere. So we derived all of these equations. So these equations were for one dimension. Then we also derived equation for three dimension, x, y, z. Okay, x, y, z. Again, steady state, transient, steady state, no heat generation. For a cylinder, for a sphere. Then we studied initial and boundary condition. If you want to solve heat transfer in any object, first you need initial or boundary condition. Okay, there will be at least minimum 2 boundary condition in any question. Okay, so when you are reading a question, first you should identify which type of boundary condition is applicable here. Okay, so there are 6 types of boundary condition. And generally you will be seeing first specified temperature, specified heat flux, convection and radiation. These 2 are okay, and 6 as well. Interface is not that common. Okay, so then we went through all sort of boundary conditions. Specified temperature, when the temperature is specified in the problem, in the question, right? That is a specified temperature boundary condition. When the heat flux is specified, right? Insulated means there will be no heat transfer on that boundary. Alright? Thermal symmetry, this is also not that common, but yeah, this is also one sort of boundary condition. Convection boundary condition, very common. Okay, we saw these numericals, interface, generalized. Okay, this we solved, this we solved, this I asked you to solve. This is very similar to this one, to 11. And then I solved this numerical and there was a calculation mistake, so I'm going to solve it again. Okay. saying consider the base plate of a 1200 watt household iron that has a thickness of 0.5 centimeter. Okay. Base area is given, thermal conductivity is given. When the thermal conductivity is given, it means it's constant, it's not changing. Okay, so the formula that we will use, it should have thermal conductivity constant. The inner surface of the base plate is subjected to uniform heat flux generated by the resistance heater inside, and the outer surface loses heat to the surrounding at T infinity by convection. So this is iron, right? And this you connect to electricity, right? There is a heat flux at this side, and the heat is losing from this side by convection. Okay, so this plate you can consider as plain wall, right? This plate can be considered as a plain wall, and this is heat flux, right? You connect it to the electricity and heat is generated, so heat flux boundary condition is applied here, specified heat flux, and the heat is lost outside by convection. Okay, inside this is a solid, the heat transfer is by conduction. Okay, so what are they asking? Taking the convection heat transfer coefficient is given, and disregarding heat loss by radiation, there is no heat loss by radiation, only convection. Obtain an expression, okay? Obtain an expression for the variation of temperature in the base plate and evaluate the temperature at the inner and outer surface. So first you have to identify which differential equation, okay? So you have 5 differential equation for plain wall, okay? And the heat transfer is happening only in one direction, x direction, right? So you go here, right? You identify which differential equation will be used, then you identify the boundary condition, and then you solve that differential equation for that iron case, okay? Specifically for that iron case. Okay, alright. So in this one, thermal conductivity is constant in that numerical, right? Thermal conductivity is given. So you cannot use this equation. Variable conductivity is not applicable in that numerical. Then you have constant conductivity, okay? In that numerical, the temperature is not changing with time. It is steady, okay? So this equation not applicable. Steady state, there is no heat generation mentioned in that iron case, in that numerical. So this one, no as well, okay? Again, temperature is not changing with time, so it's not transient. So this one, no as well. This is steady state, no heat generation. Alright, so we will use this differential equation for this question. Alright, then the boundary conditions are given, and then we will solve that differential equation for this case. So those differential equations are general equation. Okay, they are applicable to any plane wall that has steady state, no heat generation and transient heat transfer, right? But we want to find out one equation that is only applicable for this case, okay? Which is a unique solution for this case only, alright? flux is heat transfer rate divided by the area. If you remember from chapter 1, heat flux is heat transfer rate divided by the area. Okay, so this boundary condition is applied here on this side. This side is convection. Okay, convection boundary condition. So this is heat flux. Second is convection. Convection boundary condition. It is applied. It is applied here at the L coordinate. Okay, L coordinate is this. L temperature here, T infinity temperature outside of the air. So we have two boundary conditions. Every question will have at least two boundary conditions. Okay. Then we need a differential equation, general differential equation. Okay. So it's a steady state. This question is steady state. Okay. Means temperature is not changing with time. Okay. Thermal conductivity is constant. When thermal conductivity is given, that means it's constant. It's going to be that value throughout the heat transfer. Okay. No heat generation. So all of these we see, and then we see now we will solve this differential equation. We need one equation that is only applicable for this numerical. This is a general differential equation. Any plane wall which has these attributes, these qualities, we will use this differential equation. But we need one simplified equation that is only applicable for this case. Okay? This case means when this case has these boundary condition, that thermal conductivity area is that, so we need one equation that is only applicable only for this numerical. So let's solve this like we did last time. So we need one equation, right? Now it's a differential equation. So we'll try to. So we differentiate it once. So we have one equation, but we need to find out the value of C1 and C2. Now we will use the boundary condition to solve the value of C1 and C2, to find out the value of C1 and C2. So again, in your book, the method that they have used is different. I'm going to use a different method. That's why the calculation mistake happened last time. So if you want to solve it like this, you can solve. If you want to solve it like this, like my way, you can also solve. So we will use the boundary conditions, right, to solve to get the value of C1 and C2. So we use this boundary condition. Okay. C1. Okay. question was asking obtain an expression. Okay. So when you have the value of C1 and C2, right? You put the value of C1 and C2, you also have the value of L. This is not X, this is multiplier. Okay. So this equation is a general, not a general equation. This equation is a unique solution for this case. Okay. Alright. So in every question, what we do is first we read the we know it's a plane one, then we know it's a steady state, thermal conductivity is constant, and no heat generation. Okay, all of these things leads to this. Okay, the differential equation for a plane one, when these things are given, we use this. Okay, now we need a unique solution. For that we have to integrate. Okay, we have to find out one linear equation. So we integrated once, we have C1, we integrated twice, we get this. Okay, this is integration 1. This is integration. Now you have this equation which you will always get when you are solving this, but we need the value of C1 and C2. And this is going to be different. The value of C1 and C2 and x is going to be different for every equation. So you need to find out these. Now in order to find out the value of C1 and C2, we use the boundary conditions. Okay, and these boundary conditions will be different for every case. Even if it's a plane one, boundary conditions will be different. The value of thermal conductivity, convection going to be different. Right? So from the question we know heat flux is heat transfer rate divided by the area. Okay, so we can find out the value of heat flux. The second boundary condition is convection boundary condition. Convection is equal to convection. Okay, so we solve this. We see we can input this boundary condition into this. Okay, dt over dx is q divided by k. Q divided by k equals to C1. We know the value of Q, we know the value of K from the question. We have the value of C1. Alright. From equation 2, this equation, again we know dt over dx can be written as C1. dt over dx can be written as C1. dt over dx can be written as C1. Then we have the value of h is given in the question. Value of T infinity is given in the question. Value of K is given. C1 we just find out from here. You input everything here and we find the value of Ta. We have the value of Ta. Okay. Now you input the value of Tl and C1 and you will get the value of C2. L is given. Okay. So the last time that the mistake I did was I did not change it into meters. So the value of C2 was wrong in the last class that I solved. Okay. We have the value of C2. Now you input everything in this equation. Okay, you get the value of T. You can take a picture of this.
What is the difference between Q, upper Q and small Q?
This Q is heat transfer rate. This is heat transfer rate divided by area. This is heat transfer rate. This is heat flux. Small q.
So we can change by substitute
No, no. If you divide this by A is area. You get this. Understand? You have to divide this by area. This is heat transfer rate. And if you divide it by area, you will get heat flux.
So whatever the numerical is given in the slides, in the presentation, you solve those. You also solve the assignment questions. Okay, very important. in this question, it's a sphere. They have written in the question, it's a sphere. So you will use the differential equation for sphere, not for plane wall, right? Consider a spherical container of inner radius is given R1, outer radius is given R2. Thermal conductivity is given. It means thermal conductivity is constant or variable. Thermal conductivity is constant or variable in this case. Constant, right? Because it's given. The inner and outer surface of the container are maintained at constant temperature T1, T2 respectively as a result of some chemical reaction occurring inside. Obtain a Jordan relation for the temperature distribution inside the shell under steady condition and determine the rate heat loss from the container. So first tell me which differential equation is applicable for this numerical, and then tell me the boundary conditions. Which boundary conditions are given? So let's start with the boundary condition, right? So we have 6 types of boundary condition, okay? This, right? So in that numerical, what boundary condition is given? Specified temperature, right? Because this numerical is saying the temperature maintained at constant temperature T1, T2. Temperature is given. There is no mention of heat flux, right? So no boundary condition for heat flux, no mention of convection, no mention of radiation, no mention that it's an interface boundary condition, no mention thermal symmetry. Okay? And every question have at least 2 boundary conditions. So in this numerical, the boundary condition are specified temperature, which is T1 and T2. Now tell me which differential equation for spherical. So you have these differential equation. Right? So in that question, the thermal conductivity is constant. So we cannot use the first equation, right? This equation not applicable. In that numerical, there is no mention of heat generation. Right? No mention of heat generation, and the temperature is also not changing with time. So we cannot use this equation. Again here, we cannot use this as well because that question does not have energy generation information, right? Second is transient no heat generation. The heat transfer is not transient. It's not changing with time. This capital T is temperature. Small t is time. It's not changing with time in that numerical. Okay? We only have this case that is applicable. Right? So, here. Read it again. Understand why we are using that differential equation. And also read again why there is only this boundary condition. Right? So once you have the differential equation, once you have the boundary condition, you can solve it, right? It's just simple calculus. You just have to same method. You have to find out C1 and C2.
simple calculus. So we integrate it once. Now we need to find out values given in C2, just like the previous question. Okay. So you input these values. You solve these two and you find out the value of C1 and C2 from here and then just input here. So I'm skipping steps. You can do simple calculation. Okay. So this is a general equation which is only applicable for this case. The second part of the question is asking determine the rate loss. Okay. So rate loss is capital Q. When it's asking heat flux, then it's small q. Right? So this question is asking heat loss. Heat loss in this case is by conduction, so Q. If you divide it by A, it becomes heat flux. Okay? Right now they are only asking Q. K is given. Area
So the last topic of this chapter is heat generation. So let's suppose you are giving heat generation, we already studied. When you are giving any electrical, mechanical, chemical energy to a system, some heat is generated in that system, right? If you are giving heat to an oven, right? The rods in the oven, the inside of the oven will get heated up, right? So heat generation, we studied heat generation is a volumetric phenomena. It happens in the volume, okay, of that object. It's not a surface phenomena. It will happen throughout the body. So if there is a heat generation inside a body, we would want to know the heat loss from that body in that case, right? So let's suppose you have this spherical shape here. Heat is generated inside this sphere, okay? Maybe you plugged something to it, and the heat generated will be lost to the surrounding by convection, right? So the heat is generated inside this body and it will be lost outside by convection, okay? So the first equation here is for heat generation, which is generated inside. So it is equal to the heat generation per unit volume. This equation we have already studied, right? It will be equal first and second, from first and second. Second equation is heat loss by convection. From Ts is the surface, to T infinity is outside. Okay. So if you compare first and two, you will get this equation. What is this equation saying? From this equation you can find out the surface temperature of a plane wall, of a cylinder, of a sphere. If the heat is generated inside that object, the heat will be lost outside by convection. Okay, if you want to know the surface temperature of that object, of a plane wall, of a sphere, of a cylinder, in a case when there is a heat generation inside it. Okay, so you can find out like this, these equations. Okay? You just input the area and volume for each shape and you will get this. Then okay, so this is for one shape, right? If you have two spheres, two concentric spheres, okay? So in the small sphere, the heat is generated and now the heat is lost to the outside sphere, not by convection but conduction, right? Because the outside sphere is also solid, right? So the heat transfer by this small sphere, okay? The heat is generated first, right? There is a heat generation in the small sphere, and from the small sphere the heat is lost, okay, or the heat is transferring to the bigger sphere by conduction only, okay? So this is what is written here. This is Newton's law of, Fourier transform law, okay? This is conduction and it is equal to the heat generation. This is heat generation per unit volume and this is conduction, okay? You keep them equal and again you will get the same values for plane wall, cylinder. So you just solve it for one and then you input different area and volumes, okay? This is for a sphere, 2 pi r L, pi r square. Okay. So we will do 1, 2 numericals and then we have one more topic which is not very important. Sometimes we have variable thermal conductivity. In almost all of the numericals you will have constant thermal conductivity because thermal conductivity depends on the temperature, right? Right now we are studying steady heat transfer. Steady heat transfer means temperature is not changing with time. If there is a drastic change in temperature with time, the thermal conductivity will change, right? Thermal conductivity will change. So variable thermal conductivity is also a real life phenomena. It's a real life fact. Thermal conductivity can definitely change. It can be variable, but again there has to be a significant temperature change in order to have a variable thermal conductivity. So most of the time you will see constant thermal conductivity only in your numericals, and also in real life when you are simulating something or solving a heat transfer, most of the time you consider constant thermal conductivity. So, okay, you will recall from chapter 1 that the thermal conductivity of a material in general varies with temperature. Okay. However, this variation is mild. Mild means very low for many material in the range of practical interest and can be disregarded. Okay. In such cases, we can use an average value of the thermal conductivity and treat it as a constant. That's why we treat it as a constant. When the variation of thermal conductivity with temperature in a specified temperature interval is large, however, it may be necessary. Okay? If the thermal conductivity is changing drastically with the temperature change, then we have to consider. Alright? And in that case, this is how you calculate the thermal conductivity. Okay? Okay, we'll solve this question first. A 2 kilowatt resistance heater wire whose thermal conductivity is given, alright, has a diameter 4 mm, length is 0.5 meter, used to boil water. If the outer surface temperature of the resistance wire Ts is 105 degrees Celsius, determine the temperature of the center of the wire. Okay. So this wire is a cylinder, right? That wire is a cylinder. Read the question again. Yeah, of course, it is very easily seen that this wire is a cylinder, right? 2 kilowatt resistance wire, thermal conductivity is given, has a diameter is this, length is this, used to boil water, outer surface of the resistance wire. Ts is given, determine the temperature of the center. Okay, so this, they are asking T0, Ts is given, R0 is given, 4K, K is also given, thermal conductivity, right? Heat generation you can find out from here. Here. If you have total heat generation, you can just divide it by volume. Let me write it down. So the wire is a cylinder, right? They are asking the temperature at the center, T0, right? And 2 kilowatt resistance heater. So that is the total heat that it can generate. You divide it by volume, you will get heat generation per unit volume, right? The formula for calculating the center temperature in a case of a cylinder is this: T0 equals to Ts, right? Plus heat generation per unit volume, R square divided by 4K. Everything is given. You just input and solve. You just have to be very careful which formula you are using. If it's a plain wall, the formula will be different. Okay? In this case, we are asking you center temperature. In example 220, they are saying there is a large plane wall of thickness 2L experiences a uniform heat generation. There is a heat generation. It's a plane wall and there is a heat generation. Determine the expression for the variation of temperature within the wall. There is a heat generation this time, but it is still steady, right? So we will use the steady state heat generation equation. This one, okay? First equation, because they have mentioned there is a heat generation here. Large plane wall 2L experiences a uniform heat generation, okay? And then they have given two boundary condition. Okay, specified temperature is given. The values are not given, but temperature is given T1 and T2. In first case, T1 is higher. In the second case, both are same. Okay. So they are just asking a differential equation. You don't have to solve it. You don't have to input any value or get any values. You just have to find out the value of C1 and C2 for two cases. Okay. So this also is very simple. This you try, okay, and now I will start chapter 3. Okay, so do the assignment from this one and we will discuss it in our next class. Let's start chapter 3, which is the most easy chapter in heat transfer. It's the most easiest chapter. Okay, so try to understand it very carefully because it's very easy. If you understand it now, you do not even have to revise it. It's very, very, very simple. So the thing is, in first chapter, we studied basic definition. Second chapter, heat conduction. Okay, in 3 shapes. 1 dimension, 3 dimension, in a plane wall, in a cylinder, in a sphere. Right? Now we are studying heat transfer in steady state. Okay, and we are going to use the analogy of electrical system. Okay. So the numericals that you will see in this chapter, okay, there will be, like if it's a plane wall, there will be a plane wall and there will be another plane wall attached to it. Okay, so do not get confused when do you have to use the heat transfer equations and when do you have to use the electrical equations. In this chapter you are going to use electrical equations. Okay, very simple, but very simple. Okay, so when you have these things given in the numerical, you will use the electrical system. Okay, whenever you see steady state, whenever your numerical is saying that the heat transfer is steady state and there is one or more layers, okay, like this, one or more layers in your numerical, and the heat transfer is steady state, there is one or more layers, then you will use a thermal resistance method, which I will tell you. Okay, but just understand why you are using and when do you have to use the thermal resistance method. So whenever you have steady state, one dimension heat flow, no heat generation, and there are layers one after other, okay, then you will use thermal resistance. So again, the problem given has like convection coefficient and whatever like this is given. In that case, you will use thermal resistance. Okay, let's see what that is. So if there is a wall and there is another wall, another layer of a wall attached to that, and I'm asking you heat transfer, okay, through that wall, and the heat transfer is steady, and there is no heat generation. Okay, so first method is, of course, you can apply directly the conduction equation, right? The second method is thermal resistance, which is very simple, very simple. If the heat transfer is transient, if there are no layers, okay, then you cannot use thermal resistance. So this thing you can study, this is the same thing. I will just show you how you can replace it by thermal resistance. Okay. So the first method is, if I'm asking you heat transfer, you can use this formula, right? Heat conduction, right? This is the conduction, heat transfer. Now you can use thermal resistance. You can replace this length and area, L and A, LKA, by a resistance. Okay, in this case I have written R wall. In thermal resistance method, you can replace this by R. Okay, that's it. So that equation will turn into T1 minus T2 divided by R, right? We replace the L divided by Ka by R, okay? This is just to explain you the difference and the common, okay, the similarity between the thermal resistance and a heat transfer resistance. So if you are calculating heat transfer from here to here, you will calculate T1 minus T2 and there is a resistance. Resistance can be the thickness of the wall, Ka divided by L, right? In electrical scenario, you will, if you want to calculate current through this wire, you will have a voltage difference and divide by the resistance. Okay, so it's very similar. You remember that thing. Okay, you replace the L divided by Ka by R. Okay, I will also write down, but yeah, just to explain. Okay, so that was conduction. If the heat loss is by convection, you will change this HAS by R convection. Okay, and if it's a radiation, you will change it by this. I will write everything down on the board as well, but wait. Okay.
So this is very simple thermal resistance phenomena that you can apply. Okay. In cases when you have those given conditions. Okay. Let's suppose you have this wall, steady state. Okay, and I'm asking you to use thermal resistance to calculate the heat transfer. So outside from T infinity 1 to T1, the heat transfer will be by convection. From T1 to T2, the heat transfer will be by from T1 and T2 will be by convection or conduction. Conduction. From T2 to infinity, again by convection, right? So you will write H1A T infinity 1 to T1 by convection, right? This by conduction, T1 to T2. This is equal to this, and this is equal to this, because heat transfer is steady. That's why we can put equal. It's steady. It's not changing with time. So this Q here is same, right? So 1 to T infinity 1 to T1 by convection, T1 to T2 by conduction, and T2 by T infinity 2 by again convection. So this is the heat transfer analogy, right? Now if I want to write it in terms of thermal resistance, how will I write it? I will write T infinity 1 to T1 by convection, right? T1 to T2 by convection. This is convection, and this is again convection. What is R convection? Sorry, R convection. R convection is 1 divided by HA. R wall is R convection, which is H divided by KA. R radiation is this. Okay. So T1 minus T2 divided by R wall convection. Ts minus T divided by R convection. Right. So T infinity 1 minus T1 divided by R convection. T1 to T2 R wall conduction, and this again convection. Understand? Understand what I'm doing? So the first most is heat transfer by convection, which is equal to heat transfer by conduction from T1 to T2. Again heat transfer by convection from T2 to T infinity 2, right? In thermal resistance analogy, we can change them. I can write T infinity 1 minus T2, I take it in denominator, 1 divided by H1A. This denominator, L divided by Ka. This denominator, 1 divided by H2A. 1 divided by H1A can be written as R convection. L divided by Ka can be written as R conduction. Okay, and then again R convection. Alright, so this is heat transfer, and then this is thermal resistance. This is much simpler. Okay, and R total T infinity 1 to T infinity 2, T infinity 1 to T infinity 2 will be R total. Agree? And this R total is convection 1, convection 2. Understand? Understand? Now it's becoming very simple. You can just write it R total. So first thing is heat transfer is steady, right? So heat transfer here is going to be equal to here is going to be equal to here. It's not changing with time. First thing is this, right? In first and second chapter, we were following heat transfer by conduction, convection and radiation. So the uppermost formulas are from your first chapter and second chapter, right? Convection, outside T infinity 1 to T1, then conduction and then again convection. Now in chapter 3, we are going to study thermal resistance. So we can replace the denominators by resistance. So in case of convection, the value of resistance is 1 divided by H1A. Okay, how we are getting it? T infinity 1, T infinity 2, 1 divided by H1A. L divided by Ka is conduction. Okay, you understand how we are getting this? Alright, and they are always equal because the heat transfer is TD. If you want to write, you can also write like this: T infinity 1 to T infinity 2 divided by R total. If I am asking you to calculate heat transfer from this side, let's suppose this is a room and this is outside atmosphere. So I can also replace this by T R total. In this case, I am calculating heat transfer from here to here. So there will be R total, and R total is convection, convection, convection. This. So you have to remember these values actually. And how do you get these values? From uppermost equations. Okay. So in thermal resistance, you will have layers. You will have layers. So let's suppose if you want to replace it by actual resistance, okay? This is how you draw resistance. This is how you draw resistance, right? So this is this side. From outside to this wall will be R convection. This is conduction 1. This is conduction 2. This is convection. Again, outside. Convection is 1 divided by HA. Conductions are L divided by AA. L divided by AA. And this is again convection. Okay. So in this chapter you will have layers. Layers. And I will be asking you to calculate heat transfer either from here to here to here, or here to here. Okay.
ข้างใน16ข้างนอก2เข้าใจ
แล้วก็ไม่บอกว่าขีดว่าอัตราการสูญเสียความร้อน
เป็นเท่าไหร่ชัดเคสอบยังไงวะเนี่ย
เราถามที่เขาเอาที่เขาคือ
นี่กูนั่งตัว
เขาไปยืนที่ไหนกันวะ
Consider a 3 meter high, 5 meter wide, and 0.3 meter thick. Thickness is 5 meter wide, 3 meter tall. Wall whose thermal conductivity is given. On a certain day, the temperature of the inner and the outer surface of the wall are measured to be 16 into surfaces. Okay, this one, and this one. Determine the rate of heat loss through the wall. Through the wall. Conduction, right? Through the wall.
they are asking heat transfer through the wall. Heat transfer in the wall from point 1 to point 2 will be by conduction, right? It's a solid. Okay, there are two ways you can solve this question and get the same answer. Your first method is heat transfer by conduction using the formula of heat transfer by conduction. Okay, so you look at here. This is the formula from chapter 1 and 2, heat transfer by conduction. Very simple, right? You have the value of thermal conductivity, you have the value of area, you have the value of T1, T2 and the L. Second method is you apply thermal resistance. In thermal resistance, what is happening? We are replacing L divided by Ka by R, right? So R is L divided by Ka, so you can also use this method. You input all the value, you have the value of R, you input the value of R here and you will get the same answer. So now you have two methods and this method is much simpler, okay, that you will see in the next examples as well. So either you can use this or this, it's same. You use this when the operation is steady state, right? So right now, even if you use the first method, it's easy, right? I mean, this is also easy. Right now it's easy. But if you have layers of walls, if you have 1 layer, 2 layer, 3 layers, then using this becomes very difficult. Solving the numerical by this method becomes very difficult. So if you have lots of layers, you can use this method, right? Understand this? Very simple, right? Now example 2, consider a 0.8 meter high, 1.5 meter wide glass window with a thickness of 8 mm and a thermal conductivity. Determine the steady rate of heat transfer through this glass window and the temperature of its inner surface for a day during which the room is maintained at 20 degrees Celsius while the temperature of the outdoor is -10. Take the heat transfer coefficient on the inner and the outer surface of the window is given this. Determine the steady rate of heat transfer Q through this glass window. Okay. And they are also asking temperature where the temperature of its inner surface. They are asking T1, temperature of its inner surface for a day during which the room is maintained at 20 degrees Celsius. Okay. So this 20 degrees Celsius is the temperature of the room. The window is T1 to T2. Okay, the window is T1 to T2. So they are asking first the heat transfer from the room to the outside. Second, they are asking the temperature at T1, surface of the window. Okay, inside.
transfer will be happening convection, convection, convection. Okay, this is your water. So we are going to use thermal resistance method. Thermal resistance method. So first we can calculate R. Okay, we need 2R convection and 1R convection. And then we will input them here. So first let's calculate R. 1. Okay, we'll use H1.
ไม่ได้ใช้เป็นมาผิดหวังว่ามันใช้ไม่ได้
สัปดาห์ก่อนไปซีเค็ดแทนไม่ได้กล่องลิ้น
ไม่รู้มันเนี่ยแพงหมดเลย
ลิ้นตรงนั้น
ซีเช็ด
โอ้โหโอ้โห
ไม่มีทอน
สาวเลย
เฮ้ยเอาละไปแล้วมันก็เป็นบางร้านแล้วแก
ลูกบนถูกไหม
ก็รู้ว่าเป็นสูงมั้ง
ลิ้นเรียกกับปูผมไม่มีเขาบอกไม่ได้บอกเขาบอกอะไรแกไม่มีก็ดีอยู่ไปจัดตัวนี้ยิ่งจะไม่ดียิ่งรีบไม่อยู่ที่ตั้งซื้อคิดไม่ได้อ่านไม่ได้ดูคิดเขาอ้างว่าเลขาแล้วก็องค์กรต่างๆว่าเนี่ยมันต้องทำโจทย์หรือว่าต้องว่าเวลาทำโจทย์แล้วมันอ่านแล้วมาฟังอาจารย์พูดว่าเมื่อตอนเช้าอาจารย์ก็พูดไปก็เรื่องเรื่องข่าวเรื่องขายตัวเ
Solve this.
รื่องขายที่จริง
You have everything. So this question is asking heat transfer through this window, right? We are using thermal resistance method. So this is the main formula. We are calculating heat transfer from T21 to T22 divided by all the resistances. Convection, one conduction, second convection. Okay? The value for R resistance by convection is H1A, H1A, and then this. So add all of these. You have T1, T2. So put that, put these, and calculate the value of Q. That will be heat transfer through this window. T2 is not, if they are asking the value of T2, you can again calculate from T infinity T2 to minus T infinity 2 divided by R convention. Q will be C. Value of Q is 266 watt. You put 266 watt here, this value, you get T1. T1 will be minus 2.2 degree Celsius. Okay. This question now more layers. Same method, but now you have more layers. So the heat transfer from here T infinity to T1 is by convection. This heat transfer from T1 to T2 will be by this resistance R1 will be by which formula will you use? For R1, this or this? Convection, right? Then you have R2. This is air. I understand. This is air, but this is inside the box. So the heat transfer will be by conduction. It's not air outside. Understand? If it's a air but it's inside, the heat transfer will be by conduction. Understand? So R2 will be by conduction. Then you have R3. It's a solid, it's a glass, convection. And R0, convection. So you calculate all the R. And what is it asking? Determine the steady rate of heat transfer. Yeah. It is asking heat transfer. So Q, you calculate all the R, right? And divide it. coefficient H1A. This is inside of the house. So the convection coefficient is different. So I denoted it by H1A. Convection coefficient H2A is outside atmosphere. It is different, H2A. K is thermal conductivity. Thermal conductivity of glass here and here is same. So K1 and K3 are same. So this is, I wrote K1 and K1. This is for air. This is air. This is glass. This is glass. This is inside of the room and that is outside of the room. Okay? Everything is given. So this K 0.78 is glass. So this and this. This is K 0.78. H1 is given inside the house, H2 is given. So you need to clear every T31 is given, T32 is given.
Any questions? Any doubt on this example? questions on this numerical? Okay. The next topic in this chapter is thermal contact resistance. So it means when you are stacking layers like this. Okay, when you are installing a window, installing a glass on your wall, or whenever you are attaching two layers, right? It's an ideal case that they are attached perfectly. Okay, there is no crack, there is no air gap. That's a perfect case. But in reality, when you attach two surfaces, there is always some air gap, or the materials are not smooth, so there are some cracks. Okay, so the air gap, those cracks, they act as a resistance. Alright, they act as a resistance, they lower the heat transfer. Right, so this is what this is saying, and that resistance is called thermal contact resistance. It happens at the contact of two layers. Okay, so when you are adding two layers, this is layer 1, layer 2. This is the ideal case when there is no gap, no crack. And this is the actual case. When you are adding two layers, there is always some gaps. Right? Those two layers are not smooth. Okay? So whenever they have these gaps, there is some air, right? And that air acts as a resistance. And this type of resistance is called thermal contact resistance. So ideally, when you are calculating the thermal resistance by convection and conduction, you should also include thermal contact resistance. Okay, ideally you should also include thermal contact resistance when you are studying heat transfer in layers, when the layers are attached to each other. Okay, so this is what this topic is saying. But in the numericals, we are not using thermal contact resistance. We are assuming there is no contact resistance. Okay, so this is the ideal case, right? And you can also measure thermal contact resistance by some experiments, so which is given here. You can read through it on your own. Okay, this is an example of a thermal contact resistance. Okay, you are calculating 1 divided by Hc. Like I said, the thermal contact resistance is happening because of the air trapped in between the contact. So that's why we are using 1 divided by H. Okay, 1 divided by H because it's in the air, right? So this is what thermal contact resistance is, and then you can calculate the thermal contact resistance. Sorry, wait. Sorry, RC is when it is written R and C, that means it's contact resistance, okay, thermal contact resistance, and we are writing it as convection, 1 divided by H. There is no A, there is no area, right, and this is by conduction. Okay. We'll keep on doing the work on the thermal resistance. Okay. So now, again, this chapter, we have layers, right? So up until now, we studied the numericals in which the layers were parallel, right? You have a plane wall, then there is a layer attached to that plane wall parallelly. Now you have a numerical in which the layers are attached vertically. Understand? There will be layers, sometimes they are attached parallelly, sometimes they are attached vertically. So in this case, the layers are attached vertically. They are solid. Heat transfer is by conduction. But the two layers are attached vertically. Okay? In the questions before we solved, the layers were attached parallelly. Right? Parallelly. Okay. So, how will you solve if the layers are attached parallelly? You can assume it as a circuit. Okay? So, I don't know if you have studied like circuit analysis, but again it's very simple. If your layers are attached vertically, you will calculate thermal resistance by conduction in layer 1, in layer 2, and then you will add those resistance parallelly. Just like when you solve the electrical system. Okay? So, okay. So let's see this example. You have two layers attached vertically and the third layer is attached parallelly. Okay. So all layers are solid. So the heat transfer is by conduction. In first layer, conduction L1 K1A. In the second layer, again conduction L2 K2A. Third layer, again conduction L3 K3A. Last layer outside is convection. Okay, HA3. Now, if you see it as a circuit, okay, in electrical system, you will see these two resistors are parallel, and the third resistance is in series. Understand? So you will add this resistance parallelly, and the summation of this parallel resistance will be in addition, in series of the third. Okay, and this is our convection. This is outside. So we will solve numericals, and you will understand. Okay, yeah, it's written here actually. Yeah. So R1 and R2 are added parallelly. R1 and R2 are added parallelly. R3 is in series, and then there is our convection, which is again in series. So before this we were adding in series, right? Everything was in series in this numerical. The layers were attached parallelly. When the layers are attached, parallelly. When the layers are attached vertically, you add them like this, R1 plus R2. Like this. And this is in series, R3 is in series, R convection is again in series like this. Have you studied circuit analysis? Any electrical subject you studied, right? You understand what is happening, right? So this is series addition. You have two types of addition, right? In circuit analysis, you either add the resistance in series or in parallel, right? So this is parallel, and this is series. This is series, this is series, and these are in series with this parallel system. So you add the resistance here parallelly, and like this, R1 and R2, and then you add it in series. And this is how you get R total for two layers, right, which are attached. Okay, I'm using a wrong word. This is parallel. They are attached parallelly, and in this case they were attached in series. They were attached in series, right? You see, this is a series system. The resistance are added in series. Okay, and this is parallel. This is parallel. Two resistors are added in parallel. Okay, so R1 and R2, if you add them parallelly, you will get this. The R total for R1 and R2 will be this: R1 R2 divided by R1 plus R2. Understand? Okay. Now we have this question which is going to make a lot of things clear. So first you look at this diagram, which is a wall, and then you see the circuit diagram for this. R1, R2, then these three layers are in parallel. And then again series. Understand? So what is happening is we are trying to study heat transfer through this wall. Okay, so heat transfer from here to here is denoted by Ri, which is convection. From here to here, again by conduction. From here to here, again by conduction. In this layer, conduction, this layer, conduction, the above layer, conduction, this layer, conduction, and then again convection. Right? But now you have to add resistances. You cannot add resistance like this. You cannot, right? What will happen? This are in series. But these three, this layer, and the above layer, they are in parallel. So you add these resistance parallelly and then again series. Understand? Okay? So this is convection, series. You have to add everything, of course, in series, but these layers are not attached to series. They are parallel. This layer, this layer, this layer. This is brick. This is the brick, and this is the layer above, below the brick, and this one is the above. Okay? So in between you have to add the bricks parallelly, and then again series and series. Okay? High, 5-meter wide wall consists of 16 centimeter into 22 centimeter cross section, horizontal brick separated by 3 centimeter thick plaster. This is plaster, 3 centimeter thick plaster. There are also 2 centimeter thick plasters layer on each side. This is each side of the brick of a 3 centimeter thick rigid form. Inner side of the wall is shown with the indoor and outdoor temperature. This temperature and this temperature is given. The transfer coefficient of the inner and the outer side here and here is given. Assuming one dimension heat transfer and risk regarding radiation, determine the rate of heat transfer to the wall. What we have to find out. Q, T infinity 1, T infinity 2, and and R total. Okay, what is R total? Convection 1. Okay. This is 4. Conduction 1. So this is this. So there are 3. First you have to understand this. And then we'll start. Okay. R conduction 1. Right? R conduction 1. R conduction 2. R parallel. So this, and that. Okay? Then R conduction 4 and R convection 2. Length is this. When you are calculating conduction here, the length is this. 6 centimeter. Okay? Sorry. So we have R convection 1. We have R conduction 1, which is this. We have R conduction. We have created one more conduction, which is this. Okay? How we are calculating the area? Area, the length, 0.25. There is this 0.25. You see, this is 22, and when you add this and that, it becomes 25. This is 22, this and that, 25. So the length of this is 25. Okay? The length of this is 1.5. The length of this is 22. This again 25. So that's why I'm using 25 of this.
side and this side. Okay, that's right. So arc adduction 2 is going to be equal to arc adduction 4. Okay, for both of them, the length is this, right? So we can I'm changing everything into meters. They are given in centimeters. Same. This and this going to be same. Why? The resistance R3 and R5 are going to be same. Why? I'm going to write L divided by KA for this and this, right? The length is same. 1.5, 1.5. K is same. A is same. So I can just calculate one and it's going to be same. For this, the K is different. This is brick. The K is different, right? So this and this is going to be same. So the value of conductivity is different. Thermal conductivity here and here. Also the area is different. The brick is 22. This and that was 1.5. Then, so this and this is same. This doubt, please ask.
Any doubt, please ask. We just have to add 3 resistances in parallel and then all resistance in series.
Okay, so this is for 25 centimeter square. Okay, to 0.25 meter square surface area, right? And the area in the question is this. Okay, so this is per 0.25 meter square, this value here. Okay, so you what is the other side?
ว่ามันตอบเนี่ยมันคือ 4.35 ต่อเลยแต่ว่าพลังงาน
So this is your per 0.25 meter square surface area, right? We are only calculating 22, 23, 24, 25. This is 2, right? So this value is for 0.25 meter square surface area. You want to, so this is the value, right? 4.37, 0.25 per meter square area. So if you want to calculate total, or if you do it from here until here as well, it's fine. Or you go one step further and 15 meter square is this. This 3 meter high, 5 meter wide, 5 into 3, 15. So this is also like here and here. We are only calculating here, this way. So you are only calculating per 0.25 meter square surface area. If you want to calculate in whole wall, which is this, 3 meter high, 5 meter wide. So you first divide this by 0.25.
per meter square
Yes, per meter square. Or you just leave it here, that's fine.
ในเรื่องความต้องการ This answer is only considered in this
Yes,
area, right?
yes.
But this is considered all.
All, yeah, yeah.
เพื่อพิจารณาให้ช่องนี้แล้วก็ที่เหลือจะ
You understand this? Why, how we are adding? You understand all of this? Right? You add this, this, this in parallel and all of these in series.
And I have a question. Q, we call all Q เลยก็ heat transfer or heat flux แค่นั้น
If you divide it by area, then it will be flux. Now this is heat transfer rate. Right?
and the unit is watt เอาเมตร
Watt. Yeah. Joules per second, because we are also considered joules per second or watt.
ก็มันจะมีฝั่งกับอะไรวะแค่ไหนอันนี้เกม this what is this called the
Heat
rate
transfer rate.
อันนี้คือ heat transfer rate ก็คืออะไรวะอัตราการแผ่
เป็นความร้อน
ถ้าเราหาไปคิวหารเอคิวเนี่ยหารเอมันจะกลายเป็นนี้แบบนี้ใช่ไหมจำในเทอร์โมแล้วที่มันแบบหารเอาวอลลุ่มของเราเรียก็ได้เป็นวอลลุ่มดอทอะไรคล้ายๆกันนะนี่คืออันนี้จะกลายเป็นฟลักซ์อีกฟลักซ์นี่ก็เป็นคิวเรียกว่าที่ทำเฟอร์เรทเลยคือมันแปลงได้ว่าในสูตรมันจะมีอะไรว่า KA แล้วว่า KA แล้วก็เดลต้า T ไปเดลต้า T นะครับแล้วแบบในสูตรพวกนี้มันสามารถแปลงมาได้คิวเยอะคิวใหญ่
มันแค่แปลงสูตรเฉยเพราะว่าไม่ใช่
Okay, so up until now we were studying heat transfer in walls. Okay, now if you want to apply this thermal resistance analogy in cylinder and sphere, and there are layers in the cylinder and sphere as well. Okay, so heat conduction in cylinders and sphere. Consider the long cylindrical layer. Two surfaces of the cylinder layer are maintained at constant temperature T1, T2, no heat generation, constant thermal conductivity, one dimension heat conduction. Okay. So ideally this will be you will calculate the heat transfer in the cylinder from T1 to T2 by conduction. This would be ideal, right? Here, from here. Then you just input the value of area, right? And you do some mathematics, and ideally you can, if you want to solve it by conduction, right? There, your formula will be this. But since we are using thermal resistance analogy, we are going to replace it by RCY, just like we were doing it in the plane wall. In the plane wall, the resistance for conduction is L divided by Ka. In cylinder, it is this. Then R2 divided by R1 divided by 2 pi Lk. Okay. And if I'm asking you to calculate the heat transfer from T infinity 1 to T infinity 2, and it's a cylinder, right? And inside this is, let's say, air or water, something, right? So the heat transfer from T infinity 1 to T1 will be by convection. From T1 to T2 will be by conduction, and again from T2 to T infinity 2 will be by convection again. Since it's a cylinder, right? So convection is 1 divided by H1A. A is area. Area in this case is 2 pi R1L, 2 pi R2L. Okay, and for the conduction, this we obtained this from here. Okay, if you have multiple layers in a cylinder, right? It's very simple. You just have to remember for the convection and conduction, and then you just have to add it. So if I'm asking you to calculate heat transfer in a cylinder, and the cylinder has layers, and I'm asking you to calculate it this way, right? So you will add convection, heat transfer by convection, conduction, 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 and then convection, right? In a cylinder, the heat transfer by convection is 1 divided by H1A. A for cylinder is 2 pi R1L. Heat transfer by conduction in a cylinder in layers is ln R2 divided by R1 divided by 2 pi L K K1. Okay, L divided by K1A for the plane wall, right? L divided by K1A for the plane wall, and ln R2 divided by R1 for 2 pi L K1 for cylinder. So you add this 3 times. There are 3 layers. So 1, 2, R3 to R2, R4 to R3, 3 times, and then convection. Formulas you can write in your A4 paper that you are allowed to carry in your exam. Okay, so this concept is clear, right, for cylinders? Okay, you have something a hot cylinder and you want to keep it hot. You don't want it to cool down very fast. So sometimes what you do, you insulate it, right? You put something outside it, so it gets insulated, right? So that's what it is about. Critical radius of insulation. So it's very important to understand how much layer you should put on a cylinder, right? Heat transfer will reduce if it's very hot and you are wrapping it in a blanket, or you are applying some layer over a cylinder. Okay, what you want that cylinder to keep warm, to keep hot, right? But if you are adding too much layer, there are chances that the heat transfer will increase. It will cool down more fast. So that is critical radius. It's very important to understand the radius of the insulation you are applying on an object. Okay, so adding more insulation, okay, to a wall or to the attic always decreases heat transfer. You want to keep something warm, so you are adding insulation. Okay, adding insulation to a cylinder, pipe, or a sphere shell, however, is different. How? Adding insulation increases the conduction resistance of the insulation layer but decreases the convection resistance. Resistance means it's going to decrease the heat transfer, right? Resistance means it's going to decrease the heat transfer. So when you are layering something, when it is saying adding insulation increases the conduction resistance. Conduction resistance is increasing, means there is less heat loss. Your cylinder will stay warm, that's what you want. But the outside, the convection resistance decreases, means, so convection depends on H1A, area. When you are adding insulation, the area is increasing. The area of the cylinder now is increasing, right? So the convection will be higher. So when they are saying decreases convection resistance is decreasing, means heat transfer by convection will be higher because resistance is decreasing. Okay. So when you are adding layers on a cylinder, its surface area is increasing, right? Area is increasing, A is increasing. Okay. So that is why it's important to know when you should stop layering the insulation. Okay, you cannot just keep on layering. So, okay. The heat transfer from the pipe may increase or decrease depending on which effect dominates. This is same. I will show you this. Okay. So this is called critical radius, right? This is R1, R2. R2 is the insulation you are applying. Okay. So this is the R1 radius of the cylinder, and you are keep applying insulation. You are increasing, right? This is the point where the heat transfer is maximum. If you are keep applying the insulation, your heat transfer will reduce. So you have to find out this value, RCR, critical radius. Okay? Just understand the concept, it's not like numerical heavy. just understand like what critical radius is. Okay, so that you can find out simply by using the thermal conductivity and convection. Okay. All right, let's do 2 more example and then this chapter is finished. 3, 7. Okay, 3, 7 you try. I will do 3, 8. 3, 9. Okay. 3, 8 is not. 3, 9. Okay, let's just do some. A 3-meter internal diameter. So the radius is 1.5 in the diagram. 2 centimeter thick stainless steel made of, okay, a 3-meter internal diameter spherical tank made of 2 centimeter thick stainless steel is used to store iced water. So the ice water is obviously 0 degrees Celsius. The tank is located in a room whose temperature is 22. The wall of the room are also at 22. The outer surface of the tank is black and heat transfer between the outer surface of the tank and the surrounding is by natural convection and radiation. There is radiation this time. Okay. The convection heat transfer coefficient at the inner and the outer surfaces of the tank are H1, H2. Okay. Determine rate of heat transfer to the ice water in the tank. Okay. Okay, so this is a tank. It is filled with ice. There is some water in it. Okay, there is some ice, some water. So the heat transfer from here to here, convection. From here to here, conduction. And then outside we have convection as well as radiation. Radiation is mentioned in the numerical. Okay, so the heat transfer outside is parallelly convection plus radiation. Okay, so
this is why this circle. It has two parts. A is asking rate of heat transfer to the association. So the room is at 22 degrees Celsius, ice is 0 degrees Celsius, heat transfer is happening from outside to inside. This is the A part. R infinity 2 is
คลิปอะไรดูไหมเขาดูคลิปบ้างเขาแปะในอะไรเนี่ยไม่แปะในคันดูแต่คลิปมันต้อง4 ชั่วโมง5 ชั่วโมงไม่คิดลองใส่ดูครับยังไงดูเลยดูกันดีกว่าใครก็พูดกันแต่น้อยมาก
ผมก็ไม่ทำให้
We did 3-7, you try 3-9, and then you have assignment, okay? So, yeah, this is very similar to the example that we did. Thermal contact resistance.
3.9เนี่ยไม่เหมือน4ครับใช่4.9เลยไม่มีตัวอย่างใน9ให้เทียบเลยอ๋อ4ได้ยินแล้วก็ได้
Okay, so we have completed 3 chapters. If you have any questions, you can ask now or in the next class. Next class we will solve the assignments first, and then we will start chapter 4. Chapter 4 will take some time. It's a lengthy chapter. Okay. Just do all the examples mentioned in the slides, in the PowerPoint, and also the assignment questions. That's it. Okay. I'll see you next Monday.